Hello and welcome to this video on solving quadratic inequalities. So in this video we'll see inequalities and statements involving the is less than, is greater than, is less than or equal to, or is greater than or equal to symbols where the highest power on my variable, it's going to still be of a single variable, but the highest power on the variable that I see is the second power, right? You're going to see a polynomial showing up here, and the highest degree is 2, right? Quadratic inequalities. So I'm just going to run through a few examples and show you different methods, different steps I would follow to find the solutions of such inequalities. So in my first example, pardon me, and in all the examples in this video, I have the following instruction. Solve the quadratic inequality, graph the solution set. Okay, so that'll be the first thing I want to do. The first thing I want to do is get it to look like this. So I have x squared plus 3x minus 10 is greater than or equal to 0. I want to get everything to one side, 0 on the other of the inequality symbol. So I'm going to get ax squared plus bx plus c on one side, 0 on the other side. Alright, kind of put it in like a standard form, and this is in that form. I have ax squared plus bx plus c, where a is 1, b is positive 3, and c is negative 10, all on one side of the inequality symbol, is greater than or equal to, and then 0 on the other. I would like to have that, just like when we were solving quadratic equations. That would be a very good start, right? Get the quadratic polynomial on one side, 0 on the other. Okay. Then, and I guess I could call this method I'm doing here, and I'll show you another way to do this afterwards, but I guess I could call this the algebraic method, where I'm not drawing any pictures. I'm simply going to be using algebra, right? leaving things the way they are with sides and manipulating expressions and no pictures. All right, then we're trying to determine, what value or values of x, what values could I replace x with so that this expression is, greater than or equal to 0. Well, the reason I want to get 0 on the other side is because when you evaluate an expression, one of 4 things can happen. Either that expression will be a positive real number, a negative real number, 0, or undefined or not real. All right. So I guess you could count that as 5 things, but I'm just going to say, so when you evaluate an expression by plugging in a real number, the result will be a positive real number, a negative real number, 0, or undefined or just simply not real. So that's why I wanted to get 0 on the other side, because of this. For this next step, I'm going to, okay, sorry about the phone ring there if you heard that. But for this second step, right, the reason I wanted to get 0 on the other side is because after I take everything on one side, 0 on the other, I'm going to find the solutions of ax squared plus bx plus c equals 0. What I'm going to try to do is determine what value, when is this expression going to be equal to 0, and then from there you're going to see it'll be easy to also determine afterwards where it'll be greater than 0 or less than 0 or undefined or not real and stuff like that. All right, so that's what I'm going to do right now for this particular example. So we have x squared plus 3x, minus 10 is greater than or equal to 0. what I'm going to do here is, step 2, I'm going to solve the quadratic equation x squared plus 3x minus 10 equals 0. All right. Now, it's in the form, that standard form, ax squared plus bx plus c equals 0, so you could use the quadratic formula here if you'd like. All right, but this one's pretty easy to solve by factoring. So x squared plus 3x minus 10, that would factor to x plus 5 multiplied by x minus 2. And then by that zero product property, either x plus 5 is 0, meaning that x would be negative 5, or x minus 2, the other factor of this product, is equal to 0. In that case, x would be positive 2. Okay, so here are the solutions to that equation, not the inequality. I mean they do work in the inequality, right? Negative 5 for x and 2 for x make this left side equal 0. And 0 is equal to 0, so it satisfies the greater than or equal to 0 part. So these are two solutions of my inequality, but there are obviously going to be plenty more, and you'll see that in a minute. Alright, so then once I've solved the quadratic equation, I'm going to then write a number line. Okay. I'm going to mark these numbers off on a number line. Mark these solutions on a number line. Alright, so I'll do that here. So here's the real number line. Okay, and our variable is x here, so I guess you could say this number line represents possible values of x. Put x next to it. And 0 somewhere, and divides positives and negatives. And as I said, I'm going to mark these numbers off. Now positive 2, right, that would be to the right of 0, so there's positive 2. Negative 5, that would be to the left of 0, there's negative 5. And what we see happening here is that the solutions to that equation I found in part 2, they break the real number line up into 3 intervals. This interval of numbers to the left of negative 5, this interval of numbers here between negative 5 and 2, and then this interval of numbers to the right of 2. So the solutions break the number line up into 3 intervals. Sorry. Or I'll just say break the number line into intervals. Right. Okay, now something I like to do is above the number line, write the expression that we had on the one side of the inequality symbol, right? The x squared plus 3x minus 10. I'll write that above the number line. And what we're going to mark off up here is I'm just going to mark off the value of this expression at certain x values, at certain inputs. So, when x is negative 5, right, the value of this expression is 0, right? So I put the number 0 there. Right? And that's not an open point. Okay, that is actually just the number 0. Okay, and I'm not doing a graph yet. Right, that is actually the number 0 and not an open point. Same thing for above the number 2. When I plug 2 into that expression, x squared plus 3x minus 10, that would also make it equal 0. Right. So, and again, this is the number 0 and not an open point. Okay, so I've marked these numbers on a number line and kind of wrote that, these numbers make the expression on the one side of my inequality equal 0. Now we're going to see what happens in all these intervals around these numbers, right? To the left of -5, between -5 and 2, and to the right of 2. So we're going to plug in a test value from each interval. And the result will be either positive or negative. The reason that is because I already told you where it's going to be 0, right? This expression, when I get the expression on the one side by itself, I already know where the expression is going to be equal to 0, and I know it's not going to be undefined anywhere, right? There's no division, you can't divide by 0 in x squared plus 3x minus 10. So I know where it's going to be 0. I know it's not going to be undefined anywhere. So the only other possibilities of those 4 I mentioned earlier are positive or negative, right? When I plug a number into this expression, it's going to be either positive or negative. All right, so let's see. So I'll make a little table for you. All right. So here's a table. I have interval, test value. We're going to pick a value that's in that interval. And then I'll say, plus or minus, right, question mark, positive or negative. So the first interval, I'm going to do, I'll go left to right. And I'll write these in interval notation as well. All these numbers, to the left of -5, that's the interval from -infinity right, up to -5, but not including -5. I'm talking about, I don't want to use -5 or 2 here. So again, parentheses, this is an interval notation. So pick a value. Say -6. All right, and then I'll test this on another sheet of paper. All right. Will the result be positive or negative? I'm going to plug this in. All right, I'm going to plug in -6 to the expression x squared plus 3x minus 10. Now you could plug it into that expression, right? We have x squared plus 3x minus 10. But remember, this is also, if you factor it, x plus 5 times x minus 2. And I don't really care exactly what the value is. All I care about is, is the result positive or negative? So when x equals -6, when x equals -6, yeah, this would be, -6 squared plus 3 times -6 minus 10. And I could figure out what that is, but it's a lot easier to do in the factored form. -6 plus 5, well, that's going to be a negative number, and I'll put like a little negative in parentheses here, times, and then -6 minus 2 is also negative. And what's a negative times a negative? It's a positive, right? Again, I don't really care what the actual value is. All I care about is the result, when I plug it into that expression on the one side of the inequality symbol, is the result positive or negative? And I'm seeing that it is indeed positive. I'll put a little plus sign there. And in fact, I'll even go back to the interval, the number line that I drew earlier, and above the values to the left of -5, I'll put the value of x squared plus 3x minus 10 should be positive for any one of those, right? And it should be. And try it out with -7, -8, -5.2, -5 million. Plug them into this expression, it will be a positive number. And the reason for that is because you already know where it's 0, right? So it can't be 0 anywhere over here. This is actually like, you'll get into this later in a later topic. The graph of a quadratic function is continuous. All right, and I'm not going to go into what that means, but just yet. But if it's 0 here and here, and I got a positive value over here, it can't be negative somewhere over here as well, because then it would also have to be 0 somewhere else over here to the left of -5. So it has to be positive this entire time for this entire interval to the left of -5. Right? And it's due to the fact that the function, the y equals x squared plus 3x minus 10 is continuous. And if you want to look that up, fine. All right, so that was to the left of -5. Now how about this next interval, between -5 and +2. So again, in interval notation, that's this interval here, right, with the parentheses, because again, I'm not including them, I'm just saying what the numbers between them. And let's pick a value. Now, we already see a value here, a nice one would be 0. How about 0? And you can pick whatever you want. But I'm going to plug in 0. All right, and then back on this here's my test page. We're looking at this expression again, x squared plus 3x minus 10. When x equals 0, I mean clearly the value is negative, right? It's -10. It's easier to see in this one. But if you plugged it in the factored form, you'd have 0 plus 5, that's positive, times 0 minus 2, that's negative. Positive times negative is negative. All right, so the result, the value of the expression for any input between -5 and 2 will be negative. So back on my number line up here, the value of x squared plus 3x minus 10 for these values between -5 and 2, I'll put it as a negative number, a little minus sign in this interval between -5 and +2. Alright, then the last interval, the only other interval that we have left, is the numbers to the right of 2, right, and that would be the interval from 2 to infinity. And I'll just say 3. Right, 3, pi, 4, 4 million, right? Anything greater than 2 would be a good test value. And I'll just say this one out loud. When x is 3, you'd have, 8 times 1. That's a positive number. A positive factor times a positive factor. And back on my number line up here, x squared plus 3x minus 10 would be a positive number. All right, and what we're going to do is I'm going to use this picture up here. You can use the picture, or you can use the table that I drew here to answer our question, right? To find the solutions of the inequality. All right. So that's part 5, I guess you could say. So step 5, solve the inequality. And they're asking us to graph the inequality on a number line as well, graph the solution set. Okay, so I'll write the inequality out again. We had x squared plus 3x minus 10, and we were asked, when is that greater than or equal to 0? Alright, so, greater than or equal to 0, that means I'm looking for when is this expression positive or 0, right? I'm going to keep my number line in my table up here. And when I see this, is greater than or equal to 0, this is basically telling me to look for zeros. Look for zeros, because of the equal to part. Also positives, right? Because of the greater than 0 part, right? All right, so I'm looking back at my picture of the number line up here. So where are the positives? Where are the pluses? Or you look in my table. So this interval, right, to the left of -5, the values in that interval, when plugged in, will satisfy this inequality, because they'll make the expression on the left side positive, and any positive number is greater than 0. But also -5 itself. All right, so not only the numbers to the left of -5, but negative 5 itself, right? So I'm going to write this down here. So the solution set, we can actually start writing out the solution set. This interval of numbers, from negative infinity up to negative 5, but be careful. I know I have parentheses here because we were only checking numbers to the left of negative 5. But, negative 5 itself does make this expression on the left side equal 0. So negative 5 is also a solution. So now I'm going to include it, right, with the little rectangular bracket. Remember interval notation. That means that negative 5 is a solution. Okay. Or, that's not the only place. Where else do I see pluses and zeros? Well, back on my number line here, there's 2 is a solution, and so are all the numbers greater than 2, right? The numbers in this interval from 2 to infinity, but including 2, right? 2 actually makes it equal 0. So we have or, right? Remember this little union symbol for or in a previous video? The interval from 2 to infinity, but including 2, right? 2 actually makes this expression equal 0. Okay. Great. So there's the solution set, written in interval notation. You could also write this in that set builder notation. Say the solutions to this inequality are all values of x such that, x is less than or equal to negative 5, or x is greater than or equal to 2, writing the inequalities that are equivalent to those interval notations. These say the same thing, and we're also asked to make a graph. Right, now that I have the solution set, let's actually make a graph, a picture of the solution set. So here's a number line, representing possible values of x, right? My variable's x here, and look at these inequalities, these intervals. Again, the number negative 5 shows up, the number 2 shows up. Now here's where I'm actually making a graph. I'm drawing a picture. So negative 5 was a solution, right? So I'll put a nice close point or a rectangular bracket on that. 2 is a solution, right? So again, a nice close point. And all the values to the left, all the values less than negative 5 are also solutions. So all these numbers, and also all the numbers greater than 2, all these numbers, 3, 4, 5, etc. Right, and there's the final part to the answer, right, what they asked me for. They wanted the graph as well. Right. All right, so that's a lot, I know, but you're just thinking of when is an expression equal to 0, and if you know where an expression is equal to 0, then everywhere else it's either undefined or unreal, or it's positive or it's negative. And since we're going to be dealing with a quadratic expression, that's not going to be undefined anywhere, all right? So, or unreal anywhere for real number inputs. So it's either going to be positive or negative, right? So if you find where it's equal to 0, you can then easily find where it's positive or negative. All right, so this was the algebraic way, right? I called this the algebraic method. And I'll run through it real quick again. Algebraic method, where I take everything to one side, get 0 on the other. Then I basically replace the inequality symbol with an equal sign and solve the quadratic equation, the expression equals 0. I then mark these solutions on a number line, and that'll break the number line up into so many intervals. I plug in a test value from each interval. You can make a table if you want, or just leave the number line and write on it like I did there. And then find the solutions, based on the way the inequality looks. You have to really pay attention to what the symbol is. Am I looking for plus signs? Am I looking for positives? Am I looking for minus signs or negatives? Am I looking for zeros? Okay, and that'll really depend on what kind of symbol you have. All right, so that was the algebraic method. All right, let me show you another way you could also solve this. All right, so let's keep this in mind, what the solutions were, right? All the numbers less than or equal to negative 5, or all the numbers greater than or equal to 2. And I'll show you a way to do this graphically. All right. So we have the same inequality. again, I'm asked to solve x squared plus 3x minus 10 is greater than or equal to 0. But this way I'm going to do it with what's called the graphical method, or do it with a graph of a quadratic function, a parabola. All right, we're going to use a parabola to help us out. And after I'm done showing you this, I mean, you can use whichever method you please, whichever method you found easier to look at, because they both give you the same result. All right, so the graphical method. So the first step would be the same. I have it already done here. You take everything to one side, 0 on the other. All right, so get your quadratic polynomial on one side, ax squared plus bx plus c on one side, and then 0 on the other side. Which is already done here, right? I've got the ax squared plus bx plus c is greater than or equal to 0. All right. Then we're going to look at the graph on the xy plane, the function y equals ax squared plus bx plus c. All right, so now I don't have a graph paper on me. I mean, I know you see the grid behind this is plastic. I don't want to write on this. So I'm going to just kind of do a makeshift one here. So I'll put up a small little xy plane. Now, while graphing this, I mean, you can find the vertex. So we're graphing, we're graphing y, and this is, label the axes. That's x, that's the y-axis. I'm graphing y equals x squared plus 3x minus 10. All right. So you can find the vertex and stuff, but as I mentioned in the algebraic method, all that really matters to me are where is the y value 0 and where is the y value positive, where is the y value negative. Where is the value of this expression equal to 0, where is the value of this expression equal to a positive number, where is the value of this expression equal to a negative number. So I'm going to find the X-intercepts and use properties to make a rough, a very, very rough sketch. And use properties of a parabola to make a rough sketch. Emphasis on the word rough. Alright, so we already found the x-intercepts, right? Remember how you find the x-intercepts? You set y to be 0. Right? So those x-intercepts, remember if I let y be 0, I solved this earlier, right? X squared plus 3x minus 10 equals 0. One of those was at -5. -5 for x would give me 0 for y. And one of those was at +2. So I plot those, say here's -5, 0, and there's +2, 0, the x-intercepts. And then what I meant by was, I plot the x-intercepts, where the y-coordinate is 0. And what I mean by using properties is, once I've got the x-intercepts, and I know it's a quadratic function, right? The graph's going to be a parabola. Look at the lead coefficient. The lead coefficient is a positive number. It's 1x squared, +1. Remember how the lead coefficient tells you which way the parabola is going to be opening. This is going to be a parabola that opens up, right, like a smiley. Has a lowest point, right? The vertex would be at the lowest point. And if it had, if it had a negative lead coefficient, it would open down. Right? So that helps me make, again, very rough. I'm not plotting any more points other than the x-intercepts. But I know the parabola's got to open up and go through these 2 points. So it's not going to do this, it's got to do this somehow, right? I don't know. And remember, it's very symmetrical about some axis of symmetry and whatnot. But I know the graph of the parabola has to do this because it has to run through these 2 points, negative 5, 0, and 2, 0. But the lead coefficient's positive, so I know it's got to be opening up, right? This has got to be the way it looks. I don't even care how low it goes. I don't care where the vertex is this time. All right, and look at this. Now let's look at the interval on the x-axis, right? Let's look at these x values. So you see how for all of these x values to the left of negative 5, you see how the y values are positive? Plus y values, I'll say. And for all of these x values, all the values, between negative 5 and 2, see how the points on the, for all the x values between negative 5 and 2, if I go to the points on the graph, they'll have minus y values or negative y values. Right. And then for all these x values here, to the right of 2, you're corresponding to these points on the graph which have positive y values again. Alright, so you see what I did on the, look at how this compares to my number line from earlier. Remember this was back when I was doing that algebraic method, so many minutes ago. I had this number line up, right, where I had a plus sign above the numbers to the left of negative 5. And I had a minus sign above the numbers between negative 5 and 2. And I had a plus sign above the numbers to the right of 2. That's exactly what's happening in this picture. The numbers left of negative 5 on the x-axis give me positive y values. That's basically what this is saying. All the x values between negative 5 and 2 give me negative outputs, right? Negative y values. That's what this number line is saying. And all the numbers to the right of 2 give me a positive y value, positive output. That's what the number line is saying. So really what I did in that algebraic method, using a number line, is pretty much exactly the same thing I just did here, only with a bigger, this is only a bigger picture. All right, and then we just look for our solutions, right? Just like when I had that number line done in the algebraic method, I look for the solutions. So now we just, we can solve and graph, right? Solve the inequality. All right, so I'm not going to make the graph of the inequality this time because you saw that already. I'll just say solve the inequality. There they are, right? This is step 3 now. Right? Solve the inequality. Just look at my graph. We're solving, where is x squared plus 3x minus 10? Where is that output greater than or equal to 0? Well, it's greater than 0, has positive y values, for x values less than or equal to negative 5 or greater than or equal to 2. I am seeing that in the graph of that parabola. Right, and so I get the same solution set I got earlier, and I can write it in that set builder notation just like I did earlier. And then the graph of the solutions, it's still only an inequality with one variable, so the graph should be on a single number line. So the numbers that satisfy this inequality are, the numbers to the left of negative 5, including negative 5, or the numbers to the right of 2, including 2. All right, this is the final graph here. So I know I used a graph earlier, but that's not the graph of the solutions to the inequality. This graph of the parabola just helped me out, just guided me to making this graph later. All right. Okay, now I'm going to do just a couple more examples where I'll do one of them. I have 2 more examples. I'll do one of them with the algebraic method and one of them with the graphical method. And again, you decide which one you like better. They end up giving you the same results. Okay, so my next example. This is another quadratic inequality, right? Polynomials, and x squared is the highest powered term. So negative x squared is greater than, if I'm reading left to right, negative x squared is greater than 2x minus 24. All right, so we could, now again, the first step, I want to, when I'm doing the algebraic method or the graphical method, was to get everything to one side, 0 on the other. Now you could subtract 2x and add 24. That's fine. If you like it on the left, that's cool. I don't know. Me personally, I like having a positive lead coefficient on polynomials. It's just a personal preference. So what I'm going to do is take everything to the right here by adding x squared. And that gives me 0 on the left, is greater than, and then over here the positive 1x squared, then the positive 2x term, then the negative 24 term. Okay, and this is exactly the same. If you're one of those people who likes having the expression on the left and the number on the right, all right, this is the same as if I were to just switch the sides. Now remember, when you switch the sides, you also flip the inequality. So if I read this way, it'd be x squared plus 2x minus 24 is less than 0. So x squared plus 2x minus 24 is less than 0, right? When you switch the sides like I did, you also have to flip the inequality symbol around. Be careful with that. All right, so I'm gonna keep with this. All right, the way it looks here, I have it in the way I want. Ax squared plus bx plus c is less than 0, right? Everything on one side, 0 on the other. All right, then comes the part where now I'm going to figure out where does this expression equal 0. All right, so I'm going to solve this equation, this quadratic equation. Where is x squared plus 2x minus 24 equal to 0? All right, so again, you can use the quadratic formula, solve by completing the square method. But again, this one is nice and factorable. They aren't always, but this factors to x plus 6 times x minus 4. All right, so when is x plus 6 times x minus 4 equal to 0? Well, by that zero product property, remember a product is only equal to 0 when either factor is 0. So x plus 6 would be 0 when x is negative 6, right, subtracting 6, and this other factor, x minus 4, would be 0 if x was positive 4. All right, so I solve that, and I put those on a number line. So here's a number line representing possible values of x, right? Our inequality had the value, had a variable x here. And I mark these numbers off, right? Negative 6 would be to the left of negative 4, positive 4. Make that expression equal 0. Then as I said before, I like to put the expression that we're looking at, we're looking at x squared plus 2x minus 24. Or if you want to write it in factored form, that's the same thing as x plus 6 times x minus 4, whatever, right? And I'm trying to find the values of that, right? Now the value of this expression is equal to 0 at negative 6. The value of this expression is equal to 0 at 4. So everywhere else, all right, look at the intervals. Everywhere else, the value is going to be either positive or negative. Right, because it's not going to be undefined and it can't be 0 anymore, right? These are the only two values that make this expression equal 0. So everywhere else it's going to be plus or minus. Alright, so I'll make that little table again. Alright, I'll make the table as well. I mean, you don't have to do both, but here's a table with the interval, a test value in that interval, and then, is the value of that expression, x squared plus 2x minus 24, is the value positive or negative? All right. So the first of these intervals is all the values, to the left of negative 6. So that would be from, negative infinity to negative 6 in interval notation like that with parentheses. So a nice test value would be, say, negative 7 or negative 8 or negative 9, negative a million, whatever you want. Now if I plug this in again, I'm just going to do this out loud. I'll plug it in the factored form. We have x plus 6 times x minus 4 for that expression. Right? If I plug in negative 7 for x, that'd be negative times a negative. A negative, negative 7 plus 6 is negative 1. Negative 7 minus 4 is negative 11. Negative times negative is a positive, right? So back in the number line and over that interval, put a big plus sign. The value of this expression is positive for any input that's less than negative 6. All right, the next interval, this space here between negative 6 and 4. All right, so the interval from negative 6 to 4. And a nice easy one in here would be 0. All right, 0 is in the interval. I'll use that as my test value. And when I plug in 0, you see I get negative 24 if you plug in the original, or if you plug in the factored form, you'd have 6 times negative 4. That is a negative number. All right, so I have negative outputs for x values between negative 6 and 4. And the last interval, the value is greater than 4. That'd be from 4 to infinity. Again, plug in a test value, say 5 or 6 or 100, so anything greater than 4. And that would be what, 11 times 1, positive. Or that'd be a positive factor times a positive factor, or you could plug it in there and you'll see that you get a positive result. So I get positive values for this expression whenever x is greater than 4. Now we look for solutions. All right, look for your solutions. Now, the inequality here, I'm looking at x squared plus 2x minus 24 when is that less than 0? So the way I have it written here, I am looking at my number line or at my chart here, at my table. I am looking for, I'm looking for a minus sign, and that's it. I'm looking for minuses, because that's negative, right? When is this expression less than 0? When is this expression negative? And there's only one set of numbers, there's only one interval of numbers that make this expression less than 0 that would actually satisfy this inequality, and that would be this interval of numbers between negative 6 and 4, but not including negative 6 or 4, right? Negative 6 makes that expression equal 0, not less than 0. Same thing for 4. It makes this expression equal 0, not less than 0. All right, so our solution set. And I could write it in this interval notation, the interval, the numbers between negative 6 and 4, but with the parentheses on the negative 6 and 4, because they're not included. They are not solutions of this inequality. Or I could write it in that set builder notation. I can plug in any x I want. And if you have an interval of numbers like this is between, your numbers between negative 6 and 4, so negative 6 is less than x, and x is less than 4 at the same time, right? X is between negative 6 and 4. And, a graph, here's a number line for possible values of x. Here's negative 6, here's 4, and we're looking at all the numbers in between them, but not including them, right? So I'll put big open points above negative 6 and 4 to say that they're not included. And the only numbers that actually are solutions to the inequality are the numbers in between negative 6 and 4. And you can test it out. Try it out yourself. Go back to the original inequality if you want, right? That's what you should do usually when you check solutions. Try it out, Take any number. Now I wouldn't do this too long because there's infinitely many numbers in here, but take any number between negative 6 and 4 and plug it in for x. And this should be a true statement. This was my original inequality. So let's try 0 again. If I plug in 0 for x, the left side would be 0. The right side would be negative 24. Is 0 greater than negative 24? Yeah, it works. Plug in negative 5, negative 4, negative 3, 1, 2, 3. Plug in pi, plug in the square root of 2, plug in negative a half, anything between negative 6 and 4 should make that a true statement. You can do that till you're blue in the face and it'll still work. All right, great. So again, there was another example where I went through solving a quadratic inequality with that algebraic method. All right, now I have one final example where I'll go through and solve it with the graphical method. All right, we're graphing a parabola to guide us. All right, so my last example of a quadratic inequality has to solve, 3x squared is greater than negative x plus 5. Again, it's not the way I like it. It's not the way I like having it look, where I want everything on one side, 0 on the other. And I like having a positive lead coefficient, so I'm going to leave the positive 3x squared on the left and move the other stuff over. All right, so that would mean I need to add x to both sides and also subtract 5 from both sides. So now the inequality looks like this. On the left side I have my quadratic polynomial. I have the 3x squared plus x minus 5. Okay, 3x squared plus x minus 5 is greater than, right, because all I did was add and subtract. It doesn't change the symbol. And then the other side is 0. Right, so I get everything to one side, 0 on the other. Fantastic. And again, I know most people like having the expression on the left, which we have here, and I had in the last two examples at the end. All right, now we're going to look at the graph on the xy plane of y equals this quadratic polynomial. Y equals 3x squared plus x minus 5. But I'm not going to go crazy graphing it. All right, I'm just going to find 2 points, right, or maybe even 1 point or no points. Maybe this doesn't even have an x-intercept, right, because a parabola doesn't have to hit the x-axis. And if that's the case, then I'll find some other points. But first, let me find the x-intercepts if it has any. All right, so x-intercepts. Does this have any x-intercepts? So we're going to set y to be 0, right? So I'm solving 3x squared plus x minus 5. When is this equal to 0? All right, now this one is not nice and factorable. All right, 3 times negative 5 is negative 15. There are no factors of negative 15 that add up to positive 1. Or you could do the b squared minus 4. You see that? I'm just going to jump to the quadratic formula here because I can't see how to factor this. So remember the quadratic formula, right? The a is 3 here. The b is positive 1. The c is negative 5. So the solutions to this are x equals, I'm not going to write it out this time. I've done it plenty in other videos. Remember, it's the opposite of b, so negative 1. Then plus or minus the square root of b squared. So 1 squared, 1 times 1 is 1. Minus 4 times a times c. Well, 4 times a is 4 times 3, that's 12. 12 times negative 5 is negative 60. Minus negative 60 would be plus 60. Okay? And then all of this divided by 2 times a, and 2 times a is 6. 2 times 3 is 6. All right, and then we go about simplifying this. Now this is negative 1 plus the square root of 61, or minus the square root of 61, all of that divided by 6. And this is the square root of a positive number, so that's real. These are 2 real solutions. So this has 2 x-intercepts. All right, and I'll write what those are here. And I'll punch them in my calculator to get a nice approximation. All right, but so here are the x-intercepts for this graph. One will be at negative 1 plus the square root of 61 divided by 6, comma 0, right, where the y-coordinate 0, and the other one will be at negative 1 minus the square root of 61, that divided by 6, and then comma 0. And like I said, I'm gonna punch that in the calculator, get a little approximation, help me out a bit. So the first one, put negative 1 plus the square root of 61 in the numerator, and then divided by 6 in the denominator. This is approximately 1.135, so between 1 and 2. And then this one here, negative 1 minus the square root of 61 all divided by 6 is approximately negative 1.468. So between negative 1 and negative 2. Alright, so when I go to graph this, again, we're looking at the graph of y equals our expression on the one side and 0 on the other. Y equals that polynomial. I'm going to make a little makeshift, XY plane here. And sorry it's not on graph paper because I'm going to make a very rough sketch. So I know that one of them is a positive number, so say here is -1 plus the square root of 61 divided by 6. There's an x-intercept. And one of these is a negative number, say it's over here. -1 minus the square root of 61 all over 6. This is about -1.486 and so on. Great. And that's all I really need to be able to make a rough sketch. That also, and which way does the parabola open? So remember what we're graphing here. We're graphing y equals 3 times x squared plus x minus 5. The lead coefficient is a positive number. Again, right? So the parabola is going to open up. Parabola is going to open up. So and if it were negative, it would open down. So if I know that these are the x-intercepts and it's opening up, it's got to look something like this. I don't know exactly where these points all are. I just know it's going to be above the x-axis here, hit the x-axis here, then below the x-axis in between them, and then above afterwards. All right. So we're seeing that, for these x values, right, from negative infinity up until this, -1 minus the square root of 61 over 6, we got positive y values, positive outputs, right? So if I was making, like in the algebraic method, if I were making that number line, I'd be putting a big plus sign over that interval. And then between these two, right, from -1 minus the square root of 61 over 6 to -1 plus the square root of 61 over 6, going to these points on the graph, right, where there are negative y values, negative outputs. So I'd put a big minus sign, right? I put a big minus sign above the interval on the x-axis on that number line if I were doing this the other way, right, the algebraic way. And the last interval here, these numbers to the right of -1 plus the square root of 61 over 6 correspond to these points where you have positive y values, right? Positive outputs. Okay, so now let's solve the inequality. All right. So here is the inequality again, and I'll just write this again on another page, and we'll use our graph of the parabola to help us out. So now we're going to be solving 3x squared plus x minus 5 is greater than 0, right? That's what we ended up with here. All right. So when I see, where is 3x squared plus x minus 5 greater than 0? Greater than 0 means positive. So where is the value of this expression going to be positive? Where are the y values going to be positive? And I'm seeing that's happening in two different places over two different intervals here. See this positive y values over these numbers, positive y values over these numbers, just not the ones in between, right? Those have negative y values. So my solution set, all the numbers to the left, but not including -1 minus the square root of 61 over 6 or this -1.468 number. All the numbers to the left of that satisfy this. They give me positive outputs, make it greater than 0. But not the number itself, not -1 minus the square root of 61 over 6 itself, because that makes it equal 0, and that's not what we're looking for. So from negative infinity up until this -1 minus the square root of 61 all divided by 6, but not including, right? So parentheses. But that's not all, right? Or, right, little union symbol, or the numbers to the right of -1 plus the square root of 61 over 6, right? Those can be positive outputs, make this expression greater than 0, but not including it, right? So again, parentheses on that, -1 plus the square root of 61 all divided by 6, and to infinity. And there you go. There's the solutions to this inequality. All right, all the values I can replace x with and make this a true statement. We could also say, do this in the set builder notation. It's, all the values of x as long as x is less than -1 minus the square root of 61 divided by 6, or, or the union, x is greater than negative 1 plus the square root of 61 all over 6, right? Just writing the inequalities that are equivalent to these interval notations. And then finally, the graph itself, right? I know we have a graph of a parabola earlier, but that's not the graph of the solutions to this inequality. This inequality involves one variable, so I should be drawing the graph on a single number line. So here are the number line representing the possible values of x. I mark off those two numbers. Right, here's negative 1 minus the square root of 61 divided by 6. Here's negative 1 plus the square root of 61 divided by 6. And all the solutions, as we said, were the numbers less than this, but not including it. So these numbers here, but again, big open point or a parenthesis over that. Or all the numbers greater than this other one, negative 1 plus the square root of 61 over 6. So again, open point, not included. That is not a solution. And all the numbers to the right of it. And there's your graph. And all three of these together mean the same thing, right? They're all this representative of the solution set to this inequality. And you can double check, right? Always check your solutions, especially, but here it's going to be harder because, again, inequalities, these have infinitely many solutions. So you could do it till you're blue in the face, but do a check of a few of them. So pick a number to the left of this. Now remember, I said it was about negative 1.468, this number. So how about negative 1.5 or negative 2, negative 3, negative 4? How about negative 2? All right, let's see. Here's the original inequality. Let's plug in negative 2 for x. This side would be 12, right? Because negative 2 squared is 4. 4 times 3 is 12. And this side would be 7. Is 12 greater than 7? Yeah, that works. So any number less than that, plug it in to the original inequality. See if it works. It should. And all the numbers over here, now this was about, I said earlier, this was about 1.135. This number, 1.135. So I'll plug in a 1.5, 2, 2.5, 2.7 pi. Let's plug in positive 2. That'd be 12 is greater than 3. That's true. All right, and again, try it out all day long. But all these numbers here, all the numbers that are described in this box, are indeed solutions of that original inequality. They make it true. And all the ones in between, all the ones that aren't drawn, do not. Right? They would fail to make that true, make it false. Right? Great. So you have two methods there for solving quadratic inequalities. Right? You just decide which one you like better. Do you like doing it the algebraic way with that number line and solving an equation? I mean, you have to solve the same equation when you do it graphically as well to find the x-intercepts. But you'll also have this guide, this little graph of a parabola to help you out as well. So yeah, again, if you like that graphical method better, do that. It's up to you. Unless you're asked specifically to do one thing or the other, but I really wouldn't worry too much about it. Just learn how to do both and pick the one you like better. All right, as I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I have found over the years that people that take the time and the effort to learn something on their own remember that material better and for longer than if they hadn't, than someone who just breezed through. And they're more proud of it for the time and effort they put in, the hard work. So read the material, right? Read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously do tons of exercises and practice problems. Practice makes progress. It's the only way you're going to get better. And check for answers to those if they're made available to you so you can track your progress, see how you're doing. And don't just give up on a problem or an exercise after one or two attempts. Very, very often there are several approaches to a problem in mathematics that that'll work for any particular problem. So if after several attempts at a problem or problems, you're still having trouble, I would actually suggest to you to read the material again, perhaps even a third time, more slowly, more deliberately. Take some notes and then later organize those notes so you can actually understand them. Because if you've been working on problems as you should, you'll probably have a better idea as to what the author wants from you in that section, or what the author finds important about the material in that section if you're seeing the problems. So then when you go back and read again, you'll know better what to look out for in the reading, or perhaps some things will pop out at you that didn't the first time through, and it'll make working on the problems that much easier. Alright, but if after that, if after several read-throughs of the material and several attempts and approaches at problems, you're still having trouble, still not clicking with you, it is not a sign of weakness whatsoever to go asking for help after that. That's what people are there for, to help you when you're stuck. Right? So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other ones out there that are better than this one. I assure you they're out there, and they're easy to find. But just keep at it. Keep practicing. Stay persistent. Don't give up. And above all, and I think this is the hardest. I think this is the hardest thing for most people. Don't be negative. Stay positive about the subject. Believe in yourself. Believe in your abilities to work through your failures and struggles and mistakes. Because it's in those moments when you're failing and struggling and frustrated that you have the opportunity to learn the most, and also learn the most deeply. Because if you can persevere, if you can persist, make it through your frustrations, push past those frustrations, and learn how to fix your mistakes, you'll remember that material far better and far longer than anyone who just got it right the first time and breezed right through it and never gave it a second thought. So please stay at it, keep at it, stay persistent, keep practicing, stay positive. All right, stay positive, believe in yourself, and I just know you'll get it. Don't give up. Thank you very much for watching.